Okay, in this session we will look at what is called as a sampling theorem. We will see how a signal which is continuous in time, that is analog signal, can be converted into a signal which is discrete in time. So, this discrete signal can later be converted into a digital signal. So, what is the process of converting an analog signal to digital signal? Before that, what are the actual steps to be taken? What is the primary step in converting an analog signal into digital signal? The primary step before that is where you have to convert a continuous time signal into a discrete time signal. For that, we use what is called as a sampling. Let us see what is this introduction of sampling. As we have seen, most of the signals are analog in nature, that is, they are continuous in time. So, when I use an analog signal for communicating, it is called as an analog communications. Similarly, when there is a digital signal, when I use a digital signal for communications, it is called as a digital communications. So, when I have to convert an analog signal into digital signal, the primary process is we have to do what is called as a sampling. Okay? In digital communications, first of all, we have to transform analog to discrete time signal is first done. Now, the first step in the digital communications is converting a continuous time signal into a discrete time signal. That is the first process, that is the first step. Now, in doing so, we have to take care, or we have to ensure that a continuous time signal is somehow converted into a discrete time signal. This process of conversion is called as sampling. Okay? The process of converting a continuous time signal to discrete time signal is called as a sampling. Okay. So, sampling, what is the sampling? As we have seen, sampling is the first process in a digital communication signal. That means, when I want to convert an analog signal to digital signal, the preliminary or the primary step is to convert a continuous time signal into a discrete time signal. So, sampling is the first step in doing so. Now, sufficient number of samples have to be taken so that the original signal is represented in its samples correctly. Also, the original signal should be recovered from its samples completely. So, what are the applications? Applications are the feedback control, digital computers and pulse modulated communication systems and so on. So, now when I do a sampling, so how do I do? We have to sample the continuous time signal in such a way that these samples must be representing the continuous time signal. That means, when I reconstruct the original continuous time signal from this sampled signal, I should be able to get back the original signal. That means, we should ensure that sufficient number of samples are taken. Sufficient number of samples are taken so that a continuous time signal is converted into a sampled signal or discrete time signal. Okay, that's the first point is that. What is that first point says? You should take sufficient number of samples so that the original signal is represented in samples correctly. Okay. So, when I sample, it does not mean that the original signal is lost. The original signal has to be protected. So, we have to see that the original signal is always there. The sample which I take should ensure that the original signal, complete representation of the original signal is done properly. So, there is a rate at which you do the sampling, that we will see shortly. So, this is sampling. And also, when I want to recover the original signal from the sample signal, I should be able to do it. So, these are the very 2 points. One is conversion of a signal into a sampled signal, and then recovery or reconstruction of the original signal from the sampled signal. So, these are 2 important points. And as far as applications are concerned, we have digital communications applications, we have feedback control applications and digital computers. These are all used in sampling theorem. Now, let us state a sampling theorem. The main focus of the sampling theorem is because we have stated one important point in the earlier slide, where we said the number of samples which we should do must be such that they represent the original signal. So, what is that number? How much should I do? What should my sampling rate? All these things are described in your sampling theorem. So, what does sampling theorem say? Sampling theorem says that a continuous time signal may be completely represented in samples and recovered back if the sampling frequency Fs is greater than 2fm, where Fs is the sampling frequency and Fm is the maximum frequency present in the signal. So, let us see this. If you see here, we are talking of 2 points in the sampling theorem. One is the construction of a sampled signal, okay, so that the original signal representation is done properly, The second is recovery of the signal from the sampled signal. That means original to sampled signal and sample signal to original signal. So, how do we do it? This is what the sampling theorem takes care of. It talks about what is called as a sampling frequency Fs, which should be greater than 2Fm. So, Fs is the rate of sampling at which I do the sampling of the continuous signal, and it should be greater than twice the maximum frequency of the original signal. So, we will read this again. Sampling theorem is very important. It states as follows again. A continuous time signal may be completely represented in its samples and recovered back if the sampling frequency Fs is greater than 2Fm, where Fs is the sampling frequency and Fm is the maximum frequency present in the signal. So, first of all, whenever you take a continuous time signal, our endeavor must be to find out what is the maximum frequency of the given signal. Once the maximum frequency of the given signal is known, then the rate at which you sample the original signal to get a sampled version of it must be twice the maximum frequency. That is, Fs must be greater than 2Fm. This is what in a nutshell the sampling theorem says. So, what are the results of this? When I sample it at Fs greater than 2Fm, the 2 points. One is I will be able to represent the original signal in a discrete form completely. Second, then I will be able to recover the original signal from the sample version. So, all this that what I have to do is sampling theorem, as per sampling theorem, Fs must be greater than 2Fm. Now, let us look at some explanation of this. So, let us represent x of t as a signal, then y of t be sampled signal. Okay, let then x of f and y of f will the Fourier transform of these signals. Then let a delta function, which is continuous strain of Dirac-Coombe function, or it is a continuous strain of impulse strain, is being used to sample the input signal. So, let that be called as a delta Ts. Ts here is a sampling time at which it is being sampling. Okay, and it is sampling at a rate of Fs for Fs hertz. Then how do you achieve sampling? Sampling rate is achieved by the product of x of t, that is the original signal, into the delta Ts of t. So, these two are combined together. So, this will give me y of t. So, y of t is nothing but x of t multiplied by delta Ts of t. Let us see this on the board. Okay, first of all, let us represent x of t here. Let us say this is a continuous time signal. So, I have some signal like this. So, this is my x of t. So, this will have a Fourier transform x of f. So, let us say the Fourier transform of that will be like this. Okay, this is my x of f, and this is the maximum frequency Fm, and this is my x of f. Now, what are we saying? We have to sample this with a delta function, isn't it, which is having a rate of Fs, that is Ts is equal to 1 by Fs. So, it is the pulse train which is having a period of Ts which is equal to 1 by Fs. Now, this we have to sample. So, let us draw it here. So, what are the samples here? So, this is the sample here. Okay. And now, this is my delta Ts of t. So, what is it we are doing? We are taking an x of t, which is a continuous time signal. This is the frequency spectrum of that, and now I am sampling this with a impulse train. So, the continuous time signal is sampled by this. So, when I sample this, you will get a discrete function, isn't it? So, this is how it sampling. So, how are we doing sampling? We said, what did we say? We said y of t is equal to x of t delta Ts of t. So, we are having a product of this. That means, let us take, you have a multiplier here, this is my multiplier, then I will give my x of t here, then I will give my delta Ts of t here, then my output is y of t. Okay, this is my y of t. Now, if you look at this, let us sample this. Now, what is it I have to do? I have to multiply these two. If you see this, the output will be okay, the output will be something like this. So, this is my discrete signal. Now, what is that we have? We have a continuous time signal. We are multiplying with the impulse train. This is what I will get. This is my discrete time signal. Okay, this is my y of t which we got here. Now, what is y of f? If you see y of f, we will understand this a little later. Y of f will like this. So, what is it we are doing? This is my y of t, okay, this is my y of t, this is the product of these two. So, how did I get y of t? I have multiplied these two, then I got y of t. The frequency spectrum is like this. So, if you see this y of f here, this is my x of f, this is y of f. If you see closely x of f and y of f is nothing but repetition of x of f. What is the frequency of repetition? Fs, 2fs, 3fs, like that. So, similarly here also. So, that means we have an function y of f which is a sample frequency domain function, which is a repetition of x of s at a repetition rate of frequency fs. So, this is how it works. I just want to just briefly summarize this again. So, we have an x of t which is a continuous time signal, then we have a frequency spectrum of that, then we have a impulse train which we are multiplying. To sample this, I have to multiply this x of t with the impulse train. So, we are multiplying this impulse train. So, we have said that y of t, that is a sample signal, is nothing but the product of x of t and delta of t. So, okay. So, we are including delta of TST here because of the period at which it is sampling, that is fs. Okay. So, now after multiplication I will get y of t and the frequency spectrum of this. So, from this frequency spectrum we can understand that y of f is nothing but a repetition of x of f with a repetition frequency of fs. So, here how I am achieving the sampling rate fs? I am achieving the sampling rate fs by multiplying x of t by delta ts of t. So, y of t is x of t delta ts of t. Next, if you look at the last figure as we have pointed out here in the last figure, y of f is nothing but x of f only, but they are repeating periodically with the frequency fs, that is nothing but fs is equal to 1 by ts. Okay. So, the rate at which I am sampling, that is fs, is decided by the impulse train which is having that period of time for which we are going to sample. And if you see the spectrum of x of f and y of f, it is very clear that y of f is nothing but a repetition of x of f with a frequency rate of fs, that is equal to fs is equal to 1 by ts. So, what is the equation for y of f? If you see here, y of f is nothing but 1 by ts summation of minus into plus infinity x of f minus n of fs. So, what does it mean? So, y of f is nothing but 1 by ts summation from minus into plus infinity x of f minus n of fs. That means, one function is existing at x of f, then the other one will be existing at fs, then 2fs, then 3fs, like this, because n is varying from minus infinity to plus infinity. So, x of f will be at fs starting from 0, then fs, next 2fs, 3fs, like that. So, this is a repetition. So, y of f is nothing but x of f which is repeating. Now, once I know y of f, I can actually retrieve back my x of t from this, because y of f also contain, y of f is nothing but x of f, isn't it? X of f and y of f, there is a relationship between y of f and x of f. So, x of t in fact can be recovered from this sample signal. Let us see some note. From the spectrum of the signal, it is clear that as long as the signal is sampled at the rate fs greater than 2fm, the spectrum repeats periodically without overlapping. So, if you see here, the spectrum is repeating here. If you look at this, the spectrum is repeating. Once this is over, then the second one is starting, isn't it? The second one is starting here. So, here the first one is ending and immediately the second frequency is repeating. This is possible because we have taken the sampling frequency as greater than 2fm, fs greater than 2fm. So, once this condition is satisfied, there is no overlapping. That means, if you look at this here, Fs greater than 2 Fm, you have this, and then second one is starting exactly where this is finished. Okay? But if that condition is not satisfied, in the sense that the sampling frequency is less than Fm, what will happen here is, there will be a, if you look at this, there will be an overlapping. That means, now if you see this, the signal recovery will be difficult. If you see here, I can actually take out one, that is my x of f. From that x of f, I can calculate x of t using inverse Fourier transform, isn't it? But when this happens, what is happening here? There is a overlap. This overlap is because I am not following what the sampling theorem says. Sampling theorem says Fs must be greater than 2 Fm. If that condition is not satisfied, there will be a overlapping. So, when overlapping happens, recovery of the signal becomes difficult. Okay. Now, the first point says, from the spectrum of the signal, it is clear that as long as the signal is sampled at the rate Fs greater than or equal to Fm, the spectrum repeats periodically without overlapping. That we have seen here, there is no overlap. The second point, the spectrum of the sampled signal extends up to infinity and the ideal bandwidth of the signal is infinite. So, if we see here, the spectrum is extending from minus infinity to plus infinity. So, if you see here, this is going on. So, the ideal sampling, what should be the bandwidth? The bandwidth is infinity. Okay, because the spectrum is extending from minus infinity to plus infinity, the bandwidth is also equal to infinity. Let us see the next point. The original spectrum is centered f is equal to 0. The bandwidth is Fm, that is a maximum frequency. Now, how do I do the recovery? The recovery is done by passing the sample signal through a low pass filter with a cutoff frequency of Fm. So, see here, if you look at this signal, this is the original spectrum. That means the spectrum of the original signal xt, that is x of f. If you see here, this signal is existing from minus Fm to Fm, that is, it is having a maximum frequency of Fm only. So, this is having so many frequencies. So, to get these from that, what is it I have to do? I have to pass this through a low pass filter, which is having a bandwidth of Fm. Once that is done, all these components will be removed and only this will be present at the output of the low pass filter. What should be the bandwidth of the low pass filter? It should be Fm, which is the maximum frequency of the signal. That means, I should pick up a low pass filter, which is having a cutoff frequency equal to the maximum frequency of the original signal, isn't it? Once that is done, we pass this y of f through a low pass filter, the output will be x of f. Fourth point, if Fs, that is the sampling frequency, is less than 2 Fm, then the successive cycles of the sampled spectrum overlap with each other. Hence, the original spectrum cannot be recovered and distortion occurs. Now, what did I say here? If this is Fs is greater than 2 Fm and this is Fs is less than 2 Fm, that means there is an overlap here. Now, when I have an overlap like this, the recovery of the original signal is not possible correctly. That means, there will be a distortion in the original signal. So, if we ensure that the sample frequency should always be greater than twice the maximum frequency, when that is done, then the distortion will not occur. But when I sample it at a rate less than 2 Fm, then I am losing some signal because of this overlapping. This results in distortion. Let us see what is called as a Nyquist rate and also what is a Nyquist interval. When the sampling rate is equal to 2 Fm samples per second, it is called as Nyquist rate. It is also called as a minimum sampling rate. Okay? Fs greater than or equal to 2 Fm or Fs is equal to 2 Fm is called as a Nyquist rate. This is the minimum sampling rate. Okay? You can go beyond 2 Fm. So, Fs can be greater than 2 Fm, but Fs is equal to 2 Fm is called as a minimum sampling rate and is called as a Nyquist rate. This is also called as a minimum sampling rate. Then, maximum sampling interval is called the Nyquist interval. It is given by Ts is equal to 1 by 2 Fm. So, once Fs is known, you can calculate Ts. This is called as a maximum sampling rate. It is also called as a Nyquist interval. So, Nyquist rate Fs is equal to 2Fm and Nyquist interval Ts is equal to 1 by 2Fm. The Nyquist rate gives us the minimum sampling rate, whereas the Nyquist interval Ts is equal to 1 by 2Fm gives the maximum sampling time. Nyquist rate Fs is equal to 2Fm. Then you have what is called as a Nyquist interval, that is Ts is equal to 1 by 2Fm. Okay. This is the minimum sampling rate. You should ensure that Fs is equal to 2Fm. If you remember the earlier figures, if you have maintained Fs is equal to exactly 2Fm, the signal repetition will not overlap, but it will repeat exactly after the ending of the first. That means there is no gap between the two signals which are being repeated. So, that is the minimum sampling rate. When I look at the maximum interval, because that is minimum sampling, the interval becomes maximum, that is Ts is equal to 1 by 2Fm. So, these two are very important, and we have to ensure that Fs is equal to 2Fm for a distortion free recovery of the original signal, and also when you ensure that Ts is automatically ensured that T is equal to 1 by 2Fm. So, this is Nyquist rate and this is Nyquist interval. Now, let us look at what is called as a reconstruction of the signal. So, what is it we have done so far? We have taken the original signal x of t, then x of t is sampled at regular intervals of time Ts by a delta function delta of Ts of t. So, we have done this. How do you sample? I have multiplied x of t by y by delta Ts of t, then I got the output which is sampled signal y of t. Now, our next step is ensure that the signal is recovered back. So, that is what we are looking at now. So, how do I reconstruct or recover the original signal back? The process of reconstructing a continuous time signal from its samples is called as an interpolation. A signal x of t band limited to Fm hertz can be reconstructed or interpolated completely from its samples when the sampled signal is passed through an ideal low pass filter of cutoff frequency Fm hertz. So, what is the process of converting or reconstructing a continuous time signal from its samples? This is called as interpolation. So, interpolation is a process where the original signal is reconstructed from the sampled signal. This is called as interpolation. Now, how do I do interpolation, or how do I recover a signal x of t from a sampled signal? Sample signal must be passed through a low pass filter with a cutoff frequency equal to the maximum frequency of the given signal Fm hertz. The maximum frequency is Fm. The low pass filter must have a cutoff frequency which is Fm hertz. So, this is how we enable the recovery of a signal back. The second point says a signal x of t band limited to Fm hertz can be constructed or interpolated completely from its samples when the sampled signal is passed through an ideal low pass filter of cutoff frequency Fm hertz. So, how do you do it? So, let us take this here. So, what is it we are talking about? We are talking about passing the sampled signal. This is a sampled signal. Okay, this is the sample signal which you are passing through low pass filter. What is the cutoff frequency of this low pass filter? Cutoff frequency is Fm hertz, where Fm is nothing but my maximum frequency. So, what is it I will get? I will get the original signal. Okay, the whole thing is called as the recovery or reconstruction of the signal, which you have termed it as interpolation. So, take the sample signal, pass it through a low pass filter whose cutoff frequency is equal to the maximum frequency, then I will get the original signal back. So, this process, whole process is called as the interpolation or reconstruction of the original signal from the sampled signal. Now, the reconstruction or the interpolation filter transfer function is expressed as h of f is equal to Ts rectangle of f by Fm. So, the transfer function of the low pass filter which we are using, or the reconstruction filter, it is also called as the interpolation filter, is equal to h of f is equal to Ts rectangle f by Fm. So, applying the inverse Fourier transforms gives ht of the low pass filter, that is h of t is nothing but you have a rectangular function, then h of t will be a sinc function. So, that is sinc function which is 2fm to a sinc omega mt. So, this is the transfer function of the low pass filter. Now, when the sampled signal is applied to the input of the filter, the output is x of t as we have seen. Each sample of the sampled signal being an impulse produces a sinc pulse of height equal to the strength of the sample. Or all the sinc pulses will get x of t. So, what is it we are doing here? Each of the sampled pulse is actually an impulse pulse. So, what will be that output? Output will be a sinc pulse whose height will be equal to the strength of the sample. The sample will have a strength. That means, if you remember here last we have seen earlier, let us say we have a sample like this. Now, this is the strength of the signal, this is the strength of the pulse. So, this strength, the strength is varying, isn't it? How is the strength dependent? This strength is dependent on the original signal, isn't it? So, this strength will be the amplitude of the sinc pulse which you are getting outside. So, h of f is this is a rectangular function, h of t will be a sinc function. Okay. These are the low pass filter characteristics. In the low pass filter, h of f is a rectangular function, so h of t will be a sinc function. And the sinc function, amplitude of the sinc function will depend on what? The strength of the sampled signal, these impulses, isn't it? These impulses are what are being fed, these sampled functions. So, this strength is the coefficient or the amplitude of the sinc pulse. That is what we have read here. So, I will read that again for clarity. Each sample of the sampled signal being an impulse produces a sinc pulse of height equal to the strength of the sample, and we add all the sinc pulses, then we will get the x of t. So, this is how we recover by using a process or recovery called as interpolation. So, basic operation of interpolation involves feeding the sampled signal to a low pass filter whose cutoff frequency is equal to the maximum frequency, then I will get the original signal back. So, what is the transfer function of the low pass filter? H of f is a rectangular function of f by fm. So, that is the rectangular function features. Now, h of t will be a sinc function whose amplitude depends on the strength of the signal that is being fed to it. That is, it is the strength of the sample is the amplitude of the sinc pulse. Now, it gets various sinc pulses. Add all the sinc pulses, we will get x of t. See here, if y of t is a sampled output of the input x of t, then what is x of t is equal to summation of k terms x of kts h of t minus kts. Okay, here h of t is a sinc function for us. So, put that here. So, it is the summation x of kts sinc of omega m t minus kts, that is nothing but summation of k terms x of kts sinc of omega m minus k pi. This equation is called as the interpolation formula. So, as you see here, x of t is nothing but summation of k terms of sinc function which are having a coefficient or amplitude equal to the strength of the input signal. So, this is how you get x of t. Now, so far we have assumed that fs has been taken a value which is equal to or greater than 2fm. That means, we are ensuring that we are either satisfying the minimum sampling rate or we are going a little beyond the sampling rate. Okay. Now, we will see what happens if I do not do the sampling at this rate of fs is equal to 2fm. If I take fs less than 2fm, it is called as undersampling. We will see what are the effects of undersampling. We will see now effects of undersampling. When a continuous time band limited signal is sampled at a rate lower than the Nyquist rate, that is fs is equal to less than or equal to 2fm, then the successive cycles of the spectrum y of f, the sample signal, y of t overlap with each other. You have seen earlier that whenever the sampling is done at a rate less than 2fm, then the spectrum of y of f of the sample y of t, there will be a overlap. That means, if you look at y of f, my sampling is fs less than 2fm. This is called as what? This is called as undersampling. Okay, when I do undersampling, what happens? There will be a overlap. Similarly, here also there will be a overlap. So, this overlap happens when I do undersampling. So, when undersampled, a phenomenon called aliasing is produced. That means this form of overlapping is known by a phenomenon called as aliasing. Okay, when aliasing happens, what happens? When aliasing happens, we will have a distortion. Okay, so let us see what is this phenomenon. Aliasing is a phenomenon in which high frequency component in the frequency spectrum of the signal takes the identity of a low frequency component in the spectrum of the sampled signal. That means this is the phenomenon where high frequency component in the frequency spectrum of a signal takes the identity of a low frequency component in the spectrum of the sampled signal. So, this results in distortion. This is called as aliasing. So, as information signal contains large number of frequencies, deciding the sampling frequency is always a problem. So, a signal is first passed through a low pass filter, then this low pass filter blocks all the frequencies above FM hertz. This process is called as band limiting of the original signals. Let us understand this. We have read this fast. If you take a signal, what happens? The signal contains large number of frequency terms. When you have so much large number of frequency terms, identifying the sampling rate is a little bit difficult. So, what is the process done? So, what we do is, whenever you have such a signal which having a huge number of frequencies, we pass it through a low pass filter having a certain frequency of FM. That means, even though the original signal is having large number of frequency components, we are limiting the number of frequency components which you are passing. This is called as a band limiting. So, what is the band I am limiting to? The band we are limiting to is decided by the low pass filter whose cutoff frequency we are assuming, or we are saying it is equal to FM. So, this process is called as band limiting. Let us read this again. As information signal contains large number of frequencies, deciding the sampling frequency is also a problem. So, the more number of frequencies you have, large number, so deciding which is the sampling frequency becomes a little difficult. So, what is that we have to do? Signal is first passed through a low pass filter. So, what is the advantage of passing through a low pass filter, or what is the purpose of passing it through a low pass filter? When this large number of frequency components pass through a low pass filter, the output is limited only at a certain band of frequencies. This process is called as band limiting. So, this process of blocking all the frequencies above FM hertz is called as band limiting of the original signal. So, original signal, large frequencies, passing it through a low pass filter, we are having a certain band of FM, the output will be frequencies which are limited to only to FM hertz. This is called as a band limiting. So, why do you do this? This low pass filter is called as a pre-alias filter, as it prevents aliasing effect. So, we have seen earlier that aliasing effect actually involves the high frequency terms taking in the form of a low frequency terms, isn't it? So, to prevent that, I use a pre-alias filter, which is nothing but a low pass filter. Earlier we have seen aliasing effect, so how to prevent that aliasing effect. So, what is that we have to do? Because it involves high frequency terms taking shape of low frequency terms and things, what is that we are doing? We are trying to limit the number of frequencies. So, I use a low pass filter. When I use a low pass filter, which is controlling the high frequency components of signal, this is called as a pre-alias filter. This is called as a pre-alias filter. To avoid aliasing, what is it I have to do? First of all, a pre-alias filter must be used to band limit the band of frequencies of the signal to FM hertz. In spite of the various frequency terms we have, when I use a pre-alias filter, I am band limiting the number of frequency terms to FM. That is one. Second is, the sampling frequency Fs must be selected such that Fs becomes greater than or equal to 2FM. So, that means Fs should be taken as greater than or equal to FM, and I am using a pre-alias filter. So, pre-alias filter helps us in calculating what is the maximum frequency of the given signal, or limiting it rather. Then I will be able to calculate a sampling rate Fs is greater than or equal to FM. This is the use of pre-alias filter is particularly useful in cases where it becomes very difficult to calculate Fs. So, what is it we have to do? Pass all those through a low pass filter, limit the number of frequency components, calculate what is the maximum frequency, which is nothing but the cutoff frequency of a low pass filter, then ensure that Fs is greater than 2FM. So, these are the steps which we have to do to prevent aliasing. So, these are called as anti-aliasing. Okay. So, aliasing, use a pre-filter and sampling rate increase to fs greater than 2fm, then you will get a signal which is free from aliasing.